Hi, Richard Walding here again. I'm just going to have a look at the next section in the standard model chapter in the text, or in the topic in the syllabus. So I've got the heading still up there, the standard model. This is from my book, New Century Physics Queensland, Unit 3 and 4. I'm going to have a look at chapters 13.2. Now, if you're not using this textbook, it's similar in all textbooks. They'll do one on forces, fundamental forces and so on. From my text, this is this text here, page 358 to 363. Now the syllabus says you should be able to list or recall describe the four fundamental forces in terms of the particles that go between them or are used for them. But the first thing to do is to list the four forces. Now, to save time, I've put up three of them. Strong nuclear force, SNF. Now, I'm just abbreviating that. You wouldn't, of course. When you're writing it in an exam, you certainly wouldn't. Electromagnetic force, EM. Weak nuclear force, WNF. And the last one is gravity. And, well, I don't need to give a symbol for that. So they're the four forces. They're the four fundamental forces. Now, what you have to be able to do is to list the forces that apply to the standard model. Now, even though they're the four forces, not all of them are described by the standard model. But firstly, let's have a look at these forces and just something about them. The two things I'd like to look is the strength of them. I think mainly the strength and the distance they operate over. So if you looked at the strength, now you won't be asked to do the strength on an external exam. All they'll ask you to do is to list the four forces firstly, and then secondly to describe them in terms of the particles that mediate them, in other words go between them. So let's do that. The strength, if you said this was had a strength of 1 unit, this thing here would be about 100th, or in other words 10 to the minus 2 100th of the strength. Okay, this one here would be about 1/10,000th. So this is 10,000 times as strong as that one, and gravity is something like 10 to the negative 39. Okay, so it's extremely weak. So one thing you could say, the order of strength for the fundamental forces is this way, going from strong to weak. Okay, so that's the first point you could make about it. Now look, you certainly won't be asked to describe any of this sort of thing. But it gives you a bit of an idea of these forces and where they apply. Now, the strong nuclear force acts within the nucleus of an atom. Now, nucleus of or even within a proton, say, the distance is in the order of 10 to the negative 15 of a metre. The same for this weak nuclear force. That acts within the nucleus of an atom, but they say it's about 10 to the negative 18 of a metre. So that's a billionth of a metre. This is infinite. So it operates from one edge of the universe to the other. And this one here, gravity, is infinite as well. Okay? So from one edge of the universe to the other edge, gravity will apply. Same with the electromagnetic force. The trouble is it's often shielded by other particles in between. So the force, even though it's an inverse square relationship, it doesn't apply because there's any positive and negative particles in between the two you're looking at will affect the strength of the force. So we say it's infinite, but that would be in a vacuum, I guess. So they're the two aspects of those four forces. Now we can look at them. We can look at these forces in terms of the forces and some of the properties, or you can look at it in terms of some of the particles or properties and then which forces apply. So we have to do it two ways. I've done it both ways in the text. I think it's useful. So we've got here a thing called the mediating particle. Now mediating particle is the particle that operates between the two. So say for instance you had two magnets like that, north and south pole, you know that they will attract each other. The question is, what's going on in that region between the two poles, north and south pole? They're attracting, but something must be happening in there. Okay, now what we say in terms of these mediating particles, there's an exchange of particles between there. Now they're called virtual photons. They're not the real photons that you think about, which come from light with a frequency and an energy and colour and all the rest of it. They're called virtual, so they've got special properties, but they're still called photons. So there's some sort of particle going between the two poles of a magnet or between two charged objects. And the same for strong nuclear force and so on. Now the mediating particle is something you'll have to know. You'll have to know for each of these three here which are the mediating particles. Now I'm going to rule this one off. We're only using the mediating particle for these three here because it's these three that apply to the standard model. Okay, I could also put, look, I'll write in here, standard model, yes, 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 gravity, no. Gravity is not included in the standard model. Scientists haven't been able to incorporate gravity and the properties of gravity and the way it works into the standard model at the moment. They're working on it. They've been working on it for a long while. Eventually they might do it. They've got a few hypothesized things here, but nothing is quite confirmed yet. Now the mediating particle for this thing here is called a gluon, G-L-U-O-N, and you think of it as gluing. I mean, that's where the name came from. It's a particle that glues basically quarks together, but we'll talk about that later. So it has the symbol G. The electromagnetic force is the photon, and it has a symbol. It's like a gamma, like that. Okay, you'll often see it in books. It looks more like a Y, but really it's got a bit of a loop at the bottom, so it's the gamma symbol. And the weak nuclear force. Now there's three mediating particles. There's the what's called the W plus, W minus, and Z. Okay, now the W is for weak. The positive and negatives talk about the electric charge, and the Z, sometimes they put a little zero after it to indicate it's a neutral particle. Now the syllabus says you should be able to name the four mediating particles for the three fundamental forces. Now 1, 2, 3, 4. So it's G, gamma, the W particle and the Z particle. Now they don't have any names, they're just W and Z. But in terms of the four mediating particles, they're the four. So don't think there's 5, even though there's 5 letters across there. Now some books, I'm not sure about Wikipedia, but some books actually say there are 5 mediating particles. So they count them as 1, 2, 3, 4, 5. Syllabus says basically the 4 mediating particles. And when I do the table the other way, you'll see it. So learn those 4. Learn the 5 particles, right? They're elementary particles. Learn them, but think of them as just the 4 groups. Okay. We should talk about what these particles act on, or what these forces act on. Now, it's a bit tricky. I don't know if I could do it here. I'll see how we go, see if we can fit it all in. What we're going to do here is do acts. Look, I might clean this up a bit so we've got a bit of room. I'll get rid of this, I think this will be easier, and because now I just want to talk about the standard model forces, so these three here, not gravity. And there's another one that I've put in the textbook, which is the Higgs boson, or the Higgs field. Now the Higgs boson, or the Higgs particle, if you like, is responsible for giving particles mass. Now, it's not a gauge boson. These things have special names, and I'll come back to that later, but it belongs to a slightly different group, and the syllabus doesn't talk about the Higgs boson, other than to, I think it mentions that in one of the activities you might like to investigate for your research investigation, something about the origins of mass and the Higgs boson. So, what I was going to do here was look at acts on, or acts between. What particles do these act between? Now, the strong nuclear force acts between quarks. That's all it is. Now, a problem arises. The name we're using for this is the strong nuclear force. Now, sometimes people call it the strong force. They leave the word nuclear out. Okay, but as in terms of the syllabus gets, I don't know if it's so much confused, but it tries to use the word in two ways. But this is the way I suggest you learn it. The strong nuclear force acts between quarks. Its name is strong nuclear force. Now, I've seen in some of the mock exams for the external exam, QCAA has once they called it the strong force, but they mean the strong nuclear force. So treat strong nuclear force and strong force as meaning the same thing. It acts between the elementary particles, the quarks. Now, the electromagnetic force is between charged particles. Now, there are charged leptons, right? Because there are some leptons, such as the electron, the mu and the tau. They're charged leptons. The uncharged leptons are the electron neutrino, muon neutrino and tau neutrino. They're uncharged. So the electromagnetic force only operates on particles that have an electric charge. So we're talking about the charged leptons and quarks. Okay? I'll say here n quarks. Because quarks all have charges, either a plus 2/3, minus 1/3, or if you're talking about the antiparticles, minus 2/3 and plus 1/3. So charged leptons and quarks and anti-quarks. Okay, it'll happen there. Now the weak nuclear force will apply to quarks. Okay, it's you'll see when you do the next chapter, chapter 14, which is about particle interactions, you'll see the weak nuclear force acts between, or acts on, quarks and between leptons. So I'll put here leptons. Now that's all leptons, right? So not just the charged leptons, but all leptons. So it's not only the electron, muon and tau, but also the electron, neutrino, muon neutrino and tau neutrino and their antiparticles. So all leptons and quarks. Okay, so what you must learn is that there are 4 fundamental forces, and you should name them. You don't have to know off by heart the strength or the range of them. I've put that up there just to give you a feeling for them. You have to know the particles that they act on, such which elementary particles. So I've written those there. This is where they'll try and trap you by giving you a multi-choice, which will say electromagnetic force acts on, and it'll give you a list, and one will be leptons, hoping to trap you into thinking, oh yeah, leptons, electrons, they're charged, but remember it's not the neutrinos, not affected by the electromagnetic force. Weak nuclear force, both, all of the particles. They'll also ask you to state the mediating particle for each of these forces. And you have to learn this off by heart. It possibly will say, list the 4 mediating particles. Now, these are sometimes also called exchange particles, okay, or mediating particles. It just means they're in the middle of 2 objects that are interacting. Mediating, just like with a meson, it's in the middle. These are the mediating particles or exchange particles, or the force particles, terms like that. So 3 for the standard model, and you'll just have to learn them as the 4 different groups, but a total of 5 different types of these particles. Now I'll give these particles a separate group name in a minute, but that's one thing I'd suggest you learn off by heart, just this bit here. But also with the fundamental forces, don't forget to include gravity. That's one of the 4 fundamental forces, but it's not a standard model force. They haven't been able to incorporate it yet. Okay, what I'm now going to do is have a look at these 4 as the heading and talk about some of their properties that way. Now, so this is the second sort of table you'll need to be able to think about. Now you might remember early on I said the standard model, there's these elementary particles and there's forces and there's matter. Now I've dealt with the matter particles, they're the quarks and leptons. I've done that. That's the first 2 sections, chapter 13.1. In chapter 13.2 I'm going to talk about these forces. Now I've done the 4 fundamental forces, but now I want to talk about the 3 forces of the standard model and these mediating particles and so on. Now the elementary particle for forces are called gauge bosons. Now this was where it gets a bit tricky. There's a special reason they have these names. Now, as far as the syllabus is concerned, you don't even have to know why they're called gauge or why they're called bosons. You just learn it as, you know, it's just off by heart, really. You don't even have to know why these names were quark and leptons. You just learn it as 2 names. So what I suggest you do is you just think the forces particles are called gauge bosons. Don't know why they're called gauge, don't know why they're called bosons, they just are. You won't be asked any more than that in the external exam. You know, if you're doing it for a research assignment, research investigation, you know, then of course you'd need more detail. And in the text I've gone into it. Boson is, I'll just tell you briefly, boson is a special word named after that Satyendra Bose that I was telling you about, the Bangladeshi physicist, and it's to do with their spin. Now the spin is not, I mean originally they thought of a particle like one of these bosons or these quarks or leptons as actually spinning on their own axis, and that's where they got the name spin from. But now they realise it's something to do with the magnetic moment, they call, whether the magnetic moment is pointing up, and it's something that's intrinsic to these particles. Okay, it's something that's hidden, this magnetic property is hidden in these particles. And what they say is these have this hidden magnetic property, which we call spin, as a value of 1, right, or an integer value, 0, 1, 2, 3 and so on. These things have a integer value, a spin value, a spin number of 1/2. Okay, so they've got something different about the way, not so much they spin, we don't need it, just so long as you know they're divided up in terms of matter and forces. But the word boson and the other word I used before, which was fermion, is to do with this magnetic property called spin, but it's nothing to do really with spinning like a top. That's the old classical idea. This is the quantum idea, which doesn't make sense in terms of spinning particles. These are points, and points can't, well, how can a point spin? So they're bosons, the gauge word is to distinguish them from another type of boson, which is called a scalar boson, and the Higgs boson is a scalar boson. Now you don't have to know that. All you have to know is that these things are called gauge bosons. The gauge actually means something to do with measurement. The guy who coined the word gauge, it was a German who used a German word which when translated into English became gauge. So thinking of the gauge of train lines. So a thing that can measure is often called a gauge. So you have a pressure gauge, a railway gauge, and all sorts of gauges. Temperature gauge. Now, they're measuring a particular field, an aspect of the field. So if you're measuring the gravitational field, say in this room, you can take an object and move it from there to there, measure the amount of energy that took, knowing the mass and so on. You can work out the strength of the gravitational field. Or you could move it from there, which is higher, to there, and measure the change in energy, the mass, and the amount of work done, and so on. But you end up with the same value for the field. So the value of the field can be measured in different ways, but you end up with the same field, the same value for the field. The field is invariant. It doesn't depend on the gauge you use to measure it. So the same for these particles that I'm going to talk about, these photons and gluons and so on. The gluon field doesn't depend on how the gluon is measured. It's just a field independent of the way it's measured. So that's what that gauge is supposed to mean. Now, let's have a look. I'm going to rub this off and make a nice table here with the 4 gauge bosons that you have to know. So the first one is the gluon. The next one, look, I can put it in terms of the strength, but it doesn't really matter. I'm going to put here the W plus, W minus, and Z. Now that's the next group. So there's 2 bosons. There's two bosons. I should call this the gauge bosons, G-A-U-G-E bosons. Okay, and we've got the photon. I better write that in. Okay, so they're the 4 gauge bosons. 1, 2, 3, 4. Now if you like, you can think of it as 5 gauge bosons, but the syllabus will say recall the 4 gauge bosons. And all you have to do for that question, if it's a multi-choice question, it'll list a whole lot of things, and as long as you can see 1, 2, 3, 4, that's the right answer. Okay, they'll try and trap you by putting in a couple of these and say hadron or something like that as well to try and trap you. And I think they did that in the, I don't know if it was a mock exam or last year's external exam, but there's the 4. Now I'm going to call this the mediating particle. So that's those 4. I'm going to ask standard model, yes, yes, yes. Okay, so there are 3, the 3 groups are the standard model, or if you like, you can have Z as the standard model as well. If I had over here something about the Higgs boson, Higgs boson is actually a standard model, but it's not a gauge boson. It's said to be a scalar boson. So the syllabus is pretty clear about that, and they don't really ask about the Higgs boson. And if I have the graviton over, the gravity over there as another force, the proposed boson for gravity is a graviton, but it hasn't been discovered yet. It's been proposed. They know what the properties will be. They know it'll be a gauge boson. It's a vector. Its gravity's got a direction, so it'll be a gauge boson, but we're not going to include that. I'm just showing you exactly what you need for external exam now. So standard model, I'll put here the FUNDA, fundamental force, whoops, right, which fundamental force uses these. Now, this is the strong nuclear force, this is the weak nuclear force, and this is the electromagnetic. So they're the three fundamental forces, and they're the gauge bosons related to that, and they're all they all come in with the standard model. And I could say acts between. Now, the gluon acts between quarks only. That's the only thing it acts between. The weak nuclear force acts between quarks and leptons. Okay, so all quarks, all leptons, and you'll see in this chapter 14 when we do it, you'll see how this applies. Okay, I'll do some diagrams. They're called Feynman diagrams, and you'll see how all of this ties together. At the moment, this is just recall. I mean, there's nothing more to this than simple recall. Electromagnetic is, acts between charged leptons. Now, just so you've got your table right, and when you're writing this down, between, what happened there? This is between electrons, muons and tauons, and also between the antiparticles. Okay, it's not neutrinos. Okay, because they're not charged. So that's them, and we've also got between quarks. Okay, so that's that. That's quarks there, Q-U-A-R-K-S. Goodness me, something's gone wrong up here. Now, so they're the bits and pieces you have to learn for the way that's done like that. I can't see any more that you'd have to do. The listing the four bosons and the links to the forces, that's a good question. I think on the mock exam they had something like that. I think in the EA they had list the gauge bosons, these here, and I think they threw in hadron to try and trap you, but that's about it. Sorry about this. Okay, so that's the end of the stuff on gauge bosons and the fundamental forces. Okay, that's it. Thank you.